Welcome to Ask Prep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of physics, which is dual nature of radiation and matter, photoelectric effect. This concept played a crucial role in shaping quantum mechanics and changed our understanding of light and matter forever. For centuries, scientists debated whether light was a wave or a particle. Classical physics, based on wave theory, explained many properties of light, such as reflection, refraction, and diffraction. However, certain observations, especially in the early 20th century, could not be explained using the wave theory alone. One such observation was the photoelectric effect, a phenomenon in which light striking a metal surface causes the emission of electrons. This puzzling behavior led to groundbreaking discoveries that revealed light can behave both as a wave and a particle. The photoelectric effect was first observed when ultraviolet light was shined on a metal surface and electrons were ejected from it. According to classical wave theory, the energy carried by light should depend on its intensity, meaning that a brighter light should knock out electrons more effectively. However, experiments showed something completely different. Even very intense red light failed to eject electrons, while a faint blue or ultraviolet light did so instantly. This observation defied the expectations of classical physics and led to the revolutionary idea that light is not just a wave but also has particle-like properties. The explanation for this came from Albert Einstein, who proposed that light is made up of small packets of energy, now called photons. Each photon carries a fixed amount of energy, which depends on the color or frequency of light. When a photon strikes a metal surface, it transfers its energy to an electron. If this energy is sufficient, the electron is ejected from the surface. This idea introduced the concept of quantization, meaning that energy is absorbed in discrete packets rather than continuously. One of the most surprising aspects of the photoelectric effect is that increasing the intensity of light does not necessarily result in electron emission. If the light's frequency is too low, no electrons are emitted, regardless of how bright the light is. However, if the frequency is above a certain threshold, even a very dim light can eject electrons. This discovery provided strong evidence that light exhibits particle-like behavior, contradicting the classical wave theory. The implications of this were profound. It led to the realization that not just light but also matter exhibits a dual nature. This means that electrons and other tiny particles can behave both as waves and particles, depending on how they are observed. This idea was later confirmed through experiments that showed electrons can produce interference patterns, just like light waves. This wave-particle duality is a fundamental principle of quantum mechanics, shaping our understanding of the microscopic world. The photoelectric effect has several important applications in modern technology. One of the most well-known uses is in solar cells, which convert sunlight into electricity. In a solar panel, photons from sunlight strike a semiconductor material, releasing electrons and generating an electric current. This technology powers homes, satellites, and even space missions, demonstrating the practical significance of Einstein's discovery. Another application is in photodetectors, used in cameras, automatic doors, and various sensors. These devices rely on the principle that when light falls on a material, it generates an electrical response. Photodetectors are used in night vision equipment, light meters, and even in fiber optic communication systems, allowing high-speed data transmission. When light of a frequency below a certain threshold is incident on a metal surface, no electrons are emitted, regardless of the intensity. But when light of frequency higher than this threshold is used, electrons are immediately ejected. Furthermore, increasing the intensity of light above the threshold frequency increases the number of emitted electrons but does not affect their energy. This contradicts classical expectations and suggests that light must be interacting with electrons in discrete packets, or quanta, of energy. In medical imaging, photoelectric absorption is a crucial mechanism in X-ray technology. When X-rays pass through the human body, they interact with different tissues, and the photoelectric effect helps in forming clear images of bones and organs. This plays a vital role in diagnosing fractures, detecting diseases, and guiding surgical procedures. Another remarkable application is in electron microscopes, which allow scientists to view objects much smaller than what traditional optical microscopes can reveal. Since electrons also exhibit wave-like behavior, they can be used to magnify structures at the atomic level. This has led to breakthroughs in material science, nanotechnology, and biology. Beyond its practical applications, the photoelectric effect played a key role in the development of quantum mechanics, one of the most successful theories in modern physics. It challenged long-held ideas and paved the way for further discoveries, including wave-particle duality, quantum uncertainty, and the behavior of atoms and subatomic particles. Understanding the dual nature of radiation and matter helps us grasp the fundamental behavior of the universe. The fact that light and particles can behave both as waves and as discrete packets of energy is one of the most astonishing revelations in physics. It shows that at the microscopic level, nature operates very differently from what we experience in everyday life. The photoelectric effect was so revolutionary that it earned Albert Einstein the Nobel Prize in Physics in 1921. This discovery was not just a milestone in understanding light, it reshaped physics and laid the foundation for much of modern technology. As we conclude, it is important to remember that the wave-particle duality is not limited to just light and electrons. All particles exhibit this behavior, including atoms and even large molecules under certain conditions. This strange and counterintuitive property of nature is what makes quantum mechanics one of the most exciting fields of science today. Thank you, keep exploring, keep questioning, and keep learning. Stay tuned to Ask Prep for more insights into physics, and best of luck with your NEET preparation.